Assalamu alaikum. Welcome to the 9th lecture of data mining. So in the previous lecture, we had started talking about frequent pattern mining. We introduced the task of frequent pattern mining and looked at some examples, quick examples. And then we formally defined the problem of frequent item set mining, which is one particular type of pattern, item set. And subsequently, we then started discussing a scalable algorithm for finding frequent item sets, which is called the Apriori algorithm. So that is the point that we were in the last lecture. So today we will continue with our discussion with Apriori. We will discuss Apriori algorithm in detail, go over an example, and discuss some of its operations. And we will also discuss some additional types of knowledge that can be extracted from frequent item sets, specifically associations. And then if we have time towards the end, we will also discuss some extensions to the basic a priori algorithm. So that is the plan for today. So are there any questions? So I sent an email regarding your midterm exam. So I gave you the option, the date of Saturday, March 5. So it's still not finalized yet. We're also looking at the option for data mining on Friday, March 4 at 6:30 during the evening. And so please mark your calendar on the 4th and 5th. Most likely or more likely right now, it looks like on the 4th, but I'll let you know for sure in a day or two. So we are reserving the venues. So March 4 is fine, someone has said. So that's fine. So one of the good things about March 4 is that if you do it on March 4, then the NLP would be on March 5, and that time is, I think, around 1 p.m. So for those who are taking both courses, they will have some gap between the two exams. But as I said, I'll let you know for sure, because everyone seems to be now offering uh, the exams on campus, so there might be some constraints. All right. So are there any other questions or comments? So we had started discussing the a priori algorithm, which is a scalable or efficient algorithm for finding frequent item sets from transactional databases. And this algorithm uses some interesting ideas to make the algorithm efficient. So let me start from there again. We discussed this last time as well. So it uses the a priori principle, which is also similar or also known by the name of the downward closure property of the item set lattice. So essentially this means is that if an item set is frequent, then all its supersets would also be. So if an item set is infrequent, then all its superset would also be infrequent in a given transactional database. So that is a way of pruning out candidates. So next idea was basically level by level candidate generation and test approach. So level by level means that it starts from one item sets and does all the computation for those one item sets. So in a way, it's like a breadth first search. And then it generates the candidate item sets with two items. And then finds all those that are frequent there and then goes to the third and so on until it has found all frequent item sets. And while it does this generation, while it's doing this candidate generation, it does this in a systematic way. Systematic generation of candidates. So this is just done for effective or efficient generation so that generations are not duplicate and we do it in a systematic manner. And all of this can be represented as a lattice. So we discussed the lattice last time. So the top level will be 1 items, the second level will be 2 item sets, the second, third, 3 item sets, and so on. So in general, what do we have? We have I, which is a set of all possible items. Okay? So set of possible items, or you can also call this the alphabet or vocabulary. And we have the transactional database, which consists of transactions. So this is a set of transactions. And each transaction is a subset of the item set I. Okay, we talked about this last time. And we also sometimes given the minimum support threshold. So this is often sometimes taken as theta, the parameter theta. And given this, we would like to find all frequent item sets, meaning that frequent 1 item sets, frequent 2 item sets, frequent 3 item sets. So let me introduce another notation that is used in the a priori algorithm. So a priori algorithms first generate candidates, those item sets that may be potential for being frequent or are potentially frequent. And then from those candidate item sets, it actually finds the frequent item sets. So we denote C subscript K as a set of all K item sets. And actually, it's not just the set, but set of just a second. It's not just set of all K item sets. Candidate K item sets. So what is a K item set? All item set, let's say if it is C2, so it means 2 item sets. So it would be AB, for example, AC, BC, BE. So this is a set of 2 item sets. So there are 2 item sets in this set. And each item set has two items. And of course, this is the set of possible, or in this case, candidate 2 item sets. And then the other notation is basically L underscore K, sometimes also called F underscore K. So this is the set of frequent K item sets. So these are all frequent. Okay, candidate are potentially frequent, and CK would be frequent. And at the end of the day, when we say we want to find all frequent item sets, we are actually taking the union of C1, C2, sorry, not C, L1, L2, L3, up to whatever maximum LK we are able to found. So the combination of all item sets in these sets of frequent item sets is the set of all possible frequent item sets that are found from the data set. Okay. Okay, now let's go back and look at the algorithm, and then we'll look at some of its operations. Any questions so far? So this is an example of run of the Apriori algorithm. We are given a transactional database. अच्छा, किसी का क्वेश्चन है? अब्दुल्ला, आपने इसे लोअर कर दिया। चलें, ठीक है। My mic is not working. Okay, okay. So, okay. So your question is, just give me a second. All right. So the question I think was about LK and CK. So CK basically is the set of all K item set that are potentially frequent. So that's why we call them candidate. And we will get a better idea from the example. And FK or LK is a set of all frequent items. All item sets in this set are frequent. So I think better idea you get it from the example. So in this example, you have a small transactional database. The items, there are 5 items, A, B, C, D, and E. And the minimum support count, not just minimum support, is 2. When we say minimum support, it's usually presented as a fraction of the total number of transactions or a percentage. When we say minimum support count, it's an absolute integer, it's a count, it's a value. In this case, it's 2. Okay? So this is a transactional database. So there are 4 transactions. Okay? Each transaction has a set of items. So in the first pass of the a priori algorithm, you scan this database and find all one item sets, meaning single items in the database. And while you're also scanning them, you may also want to count them. And this is shown in this table. So when you scan for one item sets, all those one item sets are candidate one item sets. When you scan them, and when you count them and you find that their count is greater than 2, which is equal or greater than 2, which is the minimum support count, then they all become frequent one item sets. So candidate one item set, potentially frequent, or you can say before the counting or before pruning, and they will become frequent after you have verified that their count as well as their count in the database is greater than the minimum support count. Okay. So D has a count of 1. So this is less than minimum threshold. So according to the a priori principle, all supersets of D would also be infrequent. So in this table here, we show the frequent one item sets. And in this table, you notice that, so basically this table is L2, so L1, sorry, frequent one item sets. So there is no D there. So the table towards the left was C1, so this was L1. So we have removed D. So from this L1, we do a operation which is called self-join. I will discuss in slightly more detail later on, but that operation is called self-join, which is basically from one level to the next level. We generate the candidate 2 item sets, or C2. So this is C2. So we basically generate candidate 2 item sets in a systematic manner, and we follow a lexicographic or some fixed order. In this case, you can say alphabetical order to write the items in the item set. So AB, AC, AE, So AB, AC, AE, BC, and then CE. So these are the candidate two item sets. And then after generating the candidate, you scan the database again and count them. Go to each transaction and see if they occur in the transaction. And this is the count written on the right. So there are two item sets. In this case, candidate two item set, which have a count less than 2. One is AB and the other is AE. So both AE and AB have a count that's less than 2, which means that they are not frequent and they are not part of L2 or F2. And also, secondly, their supersets cannot be frequent, the a priori principle. So this table now is L2. So we have only the frequent two item sets here. AC, BC, and CE. Okay? And here, from here now, frequent two item sets, which is L2, we generate the candidate three item sets. Again, we will follow the self-joins operation. And in this self-join operation, as I said, we follow a systematic approach. One thing is that we always write item sets in some fixed order. And then the systematic approach is we match, for joining purposes, we match the two item sets up till the last item set, and then write the first item set, add the item from the second item set to generate the higher order item set. So in this case, for example, just to give an example, so AC, so first item is A. This is only two item sets. You will only be looking at the first item. So there is no other item set with A in the A. Then there is BC and then BE. So BB match. So to generate a new item set from this, we write BC, which is the first item set, and then add E from the second. This will give us BCE. So one candidate is generated from here. So BB has matched. So no other first items match. So no other self-join operation will occur. So our candidate three item set is just one item set, B, C, and E. We now scan the database again, and we count the number of times this particular item set occurs. And we find that it occurs twice. So now 2 is, of course, satisfying our criterion. So this is frequent. So the frequent three item set is BCE. Now this is just one item set. No further joining or growth of items is possible. Growth of item sets is possible, and that's where we stop. So what are the set of all frequent item sets? The set that are in L1, which is A, B, C. I think there was no D, and then E, and then set of frequent two item sets, which was AC, BC, BE, and CE, and the set of three item sets, which is BCE. So all of these together would be the set of all frequent item sets. So the total number of items in this transactional database was 5. The longest item set that we found frequent was of size 3, BCE. And of course, you can also look at the original transactional database. What is the longest transaction size? So 4. So there is a one transaction that has at least 4 items. So in actuality, you could have found a 4 item set that was frequent, but in this particular case, this 4 item set only occurred in one transaction, so it was not frequent. So that's why we stopped there. So if you had done this through brute force, how would have you done it? You would have generated the power set of all these 5 items. So you would have generated A, B, C, D, E, and then AB, AC, AD, and so on. So power set would be 32 item sets. And then you scan the database and count them. And then after counting, you do a filtration. But in this case, you had done, you can say, a somewhat intelligent approach, a breadth first, level by level type of approach, where you filtered out, you filtered item set that were not likely to be frequent in higher levels. So as such, you were able to stop earlier and generate all the frequent set without generating all the possible candidates from those 5 items. Okay, any question here? After this, we'll discuss some of the key steps. So any question?
सर ये आइटम सेट लैटिस क्या होता है?
Item set lattice is just a graphical representation of the items in levels. So I showed this last time. So let's say, so we have the first level is single items, A, B, let's say C, let's say we have only 3 items. So this is level 1. Okay. So at the next level, we have 2 item sets. And those 2 item sets would be generated systematically. And that systematic generation would be shown by lines. I'll just draw those lines shortly. So AB, AC, and then BC. This is the second level. And then, of course, from this second level, you can only generate one 3 item set, which is ABC. So this is the third level. Okay. So just give me a second. Just a second. ये वो मुझे फिर तंग करेगा. Just give me a second. All right. Okay. So the lattice that I drew there text-wise, I'm just going to draw the lines here. Hopefully it's visible. So let's say ये A है और ये B है आपका first level में. So from both of these, you get AB. So you draw the lines from the upper level to the lower level from which you are generating the next level item. Okay. So for example, if I had a C here, so C और फिर A से आके आपके पास AC आएगा और B और C से आपके पास BC आएगा. So if you draw this entire structure for, let's say, many items, so this is called a lattice. And for example, so AB, AC, and BC. So from here, AB and AC would give you your ABC. So why did we choose AB and AC to give ABC? Because we are following a systematic approach. We could have also generated ABC from AC and BC, or from AC and BC, sorry, from AB and BC, or from AC and BC. But we chose this because we are following a systematic order. We do not want to repeat the generation of ABC. And that approach is that we match, except the last item, we match all previous items. In this case, there are just two, so we match the first. And then we write the first item set and add the last item from the second item set to generate the higher level item set. So this is the lattice. And as I mentioned last time, on this lattice, you can draw a line. And below that line, it means that any generation below that would not be frequent. So that's why we call it downward closure. You can close it. So let's say you have an item AB, you close it here. So nothing is going to go down from here. So is that clear? All right. So there are a few things that you need to be aware of in the Apriori algorithm. So let's discuss that in slightly more detail. First of all, the candidate generation approach. Which we said it was self-join. This is the name that they used. So let's say if you wanted to generate CK, candidate K item sets, we do basically, this is generated from what they call as the self-join of K minus 1 self-joins with L K minus 1. Okay? So from the preceding frequent item sets, we generate the next candidate item set. So let me take an example here. Let's say we have, I'm writing basically C first. So A, B, C, D. This is candidate 4 item sets. Sorry, not, I'm going to write, let me write L. A, B, C, D, all right? So A, B, D, E, let's say. Maybe I should write in order. Okay, no problem. A, B, D, F, and let's say A, B, D, G. All right. So all of these are 4 item sets. And as I said, they are frequent. So from this, we want to generate. So this is L what? 4. Okay. So from this, we want to generate LC 5. Okay. So the self-join operation is, as I said, you match. So we are talking about L4. You try to match item sets whose first 3 items match. So we have 4, so first 3 items match. So if you look at this, ABCD, ABC is the first 3. Are there any other ABCs? No, this is ABD. This is also ABD. This is ABDG. So ABC doesn't match. So, but ABD, ABDE, and ABDF. So ABD is common. So from ABDE and ABDF, you can generate. So you can generate ABDEF. And also from ABDE and ABDG, ABD is common. So you can generate ABDEG. Okay? And what about ABDF and ABDG? Again, the same thing. ABDF and G can be generated. So these 3 5 item sets are generated. So of course, these are candidate. So this is the process for generation. So now, whenever you generate a candidate set, there are 2 pruning steps. First pruning step is you actually check for check each generated item set whether all its, in this case, we generated 5 item sets. So for each 5 item set, you need to see whether all its 4 subsets are actually frequent or not, which means that whether it appears in L4 or not. So let's look at that. That's the first pruning step. So for example, ABD, ABDE, इसका 4 सबसेट कौन से हैं? ABD और E है, ABD, सॉरी ABDE है और ABDF है, ठीक है, ये तो दोनों ऊपर थे, उसी से जनरेट हुआ है. बट व्हाट अबाउट ADEF? is ADEF in L4? ADEF, it's not in L4. So it is a subset of this. So if a subset of an item set is not frequent, so this is not going to be frequent also. So in this first pruning step, you are actually checking for all subsets of the previous level in that item set. And if any subset does not exist in the previous frequent item set, you delete that candidate. Okay? So A, B, D, E, F would be generated. And similarly, I think in this example, all will be deleted. So दूसरे का आप देखें A, B, D, and then we have E, G. So what about A, D, E, G is not present there. So ये भी delete हो जाएगा. And the third one, A, D, F, G, ये भी present नहीं है, ये भी delete हो जाएगा. So we have deleted all the generated candidate even before we scan the database. So this is the first pruning step. So any candidate whose basically K minus 1 subset does not appear in L K minus 1. Okay? So in the example that I showed, all 3 would have been deleted. But let's say, let me modify that example a little bit. So we had A, B, F. Okay? So A, so let's say in the, so L4 में मैं कुछ और भी ऐड कर देता हूँ, let's say. So मेरे पास है, let's say, A, B, A, D, E, F, ठीक है, and then B, D, E, F भी ऐड कर देता हूँ, let's say. So now all the subsets, 4 subsets of this 5 candidate item set now do exist in L4. Okay? So in this case, this would remain as a candidate and the other 2 will be removed. Now you scan the database for this, the count of this only. But even after, let's say, the counting, you find that the count of this in a database is less than your minimum support, it will then be pruned again. So then delete any remaining item set if its count in the transactional database does not satisfy the criteria. So 2 pruning steps. After this, you will get L5. So C5 से L5. C5 में सबसे पहले आपने देखना है कि जितने भी कैंडिडेट जनरेट हुए हैं उनके subsets, 4 subsets, 1 level less subset actually exist. If they do not exist, then you know for sure from the Priori principle, they are not going to be frequent. No need to scan the database for them. So prune them there. But let's say if there is an item set that is actually frequent, that is not pruned out, let's say, as I said in this later example, A, B, D, E, F. Then you scan the database, but if after scanning you find that the count is less than the minimum count, then it's pruned again. ठीक है? Okay, so is this clear? So we discussed two things here. One was how we generate candidates, and secondly, after generation and before counting, you have a pruning step, and then you have a second pruning step after counting from the database. So after both of these two prunings, you get to the next frequent item set, and then the process is repeated to generate the next candidate and so on. So given this understanding, so how many scans of the database would be required? So how can you answer this question? So how many scans in general would be required in a priori algorithm? So if the maximum length of item sets that is frequent that is found is k, so k or k plus 1 scans are required if the max length of frequent item set is k. So why did I write k or k plus 1? So if you look at the example, so in this case, what was the maximum length of item set that we found that was frequent? 3, right? And how many scans did we do? So we did a scan which was for the first, then we did a scan for the second, then we did a scan for the third. We did 3 scans. But let's say just hypothetically, let's say ये जो candidate हमने generate किया B, C, E, let's say scan के बाद हमको पता चला कि इसका count सिर्फ 1 है. So then of course the maximum length of frequent item set that we have found would have been 2, because ये 3 वाला तो delete हो जाएगा. So in essence 2 plus 1, 3 scans हमको करने पड़े. So if the maximum possible length of item set that you found was k, then you could have done k plus 1 item sets or scans of the database. ठीक है? So another quick question here, if you know the maximum length of a transaction, so you know that the maximum length of your frequent item sets would always be less than or equal to that maximum length of transaction. So let's say आपकी transaction जो सबसे बड़ी transaction आपके database में 10 है, तो you are never going to find an item set that is longer than 10, right? So all right. Any questions? Okay, before I move on to some other, you can say, issues. So there is another piece of information that is quite useful and that which can be derived from the set of frequent item sets. So those are called association rules. Okay. So what are association rules? So let's say you have found that an item set A, B, C is frequent. Okay. So by the way, when do we say that an item set ABC is frequent? When its support of ABC is greater than theta. So this theta here is actually an evaluation measure, which is sometimes also in data mining is called interesting inter okay interestingness. Didn't write it correctly. Interestingness measure. What happened? So support theta or this criterion and the associated measure, which is minimum support, is an interestingness measure, which is used to filter out potentially uninteresting or non-actionable patterns from our data mining algorithm. Okay? So for item sets, support is thus a evaluation measure or an interestingness measure. But I was talking about rules. So from ABC, which is frequent, you can, of course, generate rules from here. And you can generate many rules. So you can generate AB implies, for example, C. You can have A implies BC. You can write, for example, AB implies AC. And then C is equal to AB. And what else? AB ऊपर किया था मैंने. All right. So we have one more, which is what was that? We wrote AB before, so we have AC implies B, and then of course BC implies A. So all of these rules can be derived from this frequent pattern or frequent item set. So of course, again, there are multiple rules. We'll need to have some way of quantifying the interestingness of these rules. And the most common interestingness for these rules is what is known as a confidence. So for item set, it was support as an interestingness measure. For rules, the common interestingness measure is confidence. Of course, there are other interestingness measures. We'll be discussing this later on in this course, but these are the two common ones. So for example, let me take one example, confidence. So conf of the rule AB given C. So how do you compute this? So this is basically the support of A, B, C, which is the full item set, divided by the support of the condition, which is AB. So this is somewhat like the conditional probability. How likely is C to occur after AB has been observed? Okay? So support of ABC divided by support of AB. So when would this rule have a higher confidence? When the condition AB, the denominator is small, or when the whole item set is frequent, the numerator is high. Okay? So similarly, as we said, support we said when support of some item set is greater than, let's say, minimum support, we said that item set was frequent. So similarly, confidence of some rule is greater than minimum confidence, which is again a parameter, then we say the rule is strong. Okay? So we have talked about two interesting measures, one for frequent items, one for item sets. And when its support was greater than minimum support, let's say theta, we said that that item set is frequent. And we are assuming the frequent items are of interest to us. That's the whole goal in data in item set mining. The second piece of knowledge that we derived was that there were rules, association rules. And if the confidence of the rule is greater than some minimum confidence which we have specified, then we say that that rule is strong. So at the end of the day, by applying a priori algorithm, you will find the set of all item sets and the set or all strong rule, right? So two pieces of knowledge. One is item set, which is frequent. The second is rules that are strong. So by the way, why are these rules important? Just to give you an example, let's say in terms of you have a, let's say, example from a retail store. Let's say we have milk and we have tea and we have, let's say, sugar. Okay? So let's say this combination of items are sold frequently. So this item set is frequent. So from this, let's say milk, tea, and sugar. Uh, so let's say from this, I'm just trying to think of an interesting example. So if someone bought milk and tea, then he or she is more likely to buy sugar. Or in other words, if someone has bought milk and tea, then sugar is very high probability an item that would also be part of milk and tea. While some other rule, let's say like sugar, implies, let's say, or let me change this, milk implies, let's say, sugar and tea. Maybe this is not as strong. So what does this say? And how can we use this piece of information? So we have found that if people buy uh, milk and tea, then sugar is also likely to be sold with those two items. So, of course, as a retail store manager, you might want to utilize this for, let's say, cross marketing. Maybe you might put some slight discount on milk or tea because you know that whenever they buy milk and tea, they will also buy sugar. Maybe you even increase the price of sugar. You know that sugar will always be bought with them. So such kind of, you can say, business knowledge you can utilize or extract from such types of rules. So for example, let's say again, let me write this again, milk tea, suppose sugar, let's say confidence. So confidence can also be written as percentage. Let's say this is 90%. And the other that we wrote, let's say was milk, tea, sugar. I don't know what I wrote. Let's say tea and sugar implies, let's say milk. Let's say iska confidence jo tha, let's say 40%. So the first one says that if someone has bought milk and tea, then with 90% confidence, or you can say in some way probability, he is likely going to buy sugar. While the lower rule says that so tea and milk, if someone has bought tea and milk, then there's only 40% chance that he will buy sugar. Okay? Okay. So any questions so far? Any questions? Let's see. Yeah. Anyway, so no questions. All right, so now let's look at some of the issues in the a priori algorithm and some of the tricks you can say that are commonly used to improve or rectify those issues. Uh, so what are the, you can say, space and time complexity issues in a priori algorithm? So, so one thing is multiple scans of the DB. So generally, transactional databases are massive because transactions often occur at different locations with different customers, or if you talk about retail stores, so transactional databases can easily go into the millions. So, and in the a priori algorithm, as we saw, we have to do multiple scans, whole scans of the database to count items. So multiple scans is computationally expensive. Okay? So that is one issue. And another issue is basically huge candidate set. So when you generate a candidate set using the systematic approach that a priori has used, you might be generating many candidates, and that candidate size might be large, massive. So again, this is an issue of space complexity. So you'll have to save all those or retain those item sets and then ensure that you update their counter. And related to this is, of course, the tedious counting of item sets. So let's say you have 5,000 item sets that are candidate. So you'll have to track all those 5,000 item sets when you scan the database. And for each item set that you found in any particular transaction, you will increase its count by 1. So tedious counting. So counting is quite expensive computationally as well as space-wise because you have so many candidates. So anything else? I think these are primarily the main issues, and there are some tricks that we can use to alleviate these issues, which we'll discuss next. Any questions? All right. So first of all, multiple scans. Uh, so the assumption is that the TDB is massive. So the database is massive and it cannot be all loaded into memory. So whenever you do a scan are done on disk or some secondary storage, not in memory. So that's why they are expensive. Okay? And obviously you cannot bring all the transactions of the database into memory. So that is too big. So usually we don't have that much memory. Even if you go into a memory of 1 TB or 2 TB, most transactional databases or real world problems are massive. So one idea is basically partitioned a priori. So partitioned a priori algorithm. So this idea is basically, let's say I call the transactional database D. So let me partition it into two, D1 and D2. And when I say partition, this is exclusive partition, meaning that D1 union D2 is equal to D, and D1 intersection D2 is null, meaning that you basically split the two. There is no overlap, in other words, separate databases. And again, just for explanation's sake, let's say we have split to such an extent that D1 and D2 now fit into memory. Okay? So D1 and D2, you can always split it into 100, for example, portions, such that each portion fits into memory. So let's say each portion fits into memory. So if they fit into memory, you just need one scan from the external disk, bring it into memory, do all the processing of a priori and find all frequent item sets. So let's say I say fd1 is the set of all frequent item sets in D1. And similarly for fd2. Okay? And so you only needed one scan to do this. एक scan पूरा database का किया जिसमें D1 भी था और D2 भी था. Of course you can do it serially. आप serial में कर रहे हैं तो पहले D1 आप load कर लें, आधा database scan किया let's say, और उसके ऊपर आपने सारे frequent pattern ढूंढ लिए, फिर D2 load किया, उसके ऊपर सारे ढूंढ लिए. So एक ही scan eventually अभी तक हुआ of the whole database. So from here, we need to make sure that we have found all the frequent item sets in the original database, which is D. So what we do is, so for, of course, FD1 is the set of frequent item sets in D1, FD2 is set of frequent item set in D2. So can I say, for example, FD1 union FD2 is equal to FD? So in general, actually, this is not true. And I will explain shortly why. So if it is not true, what we do is we take the union as I wrote before, and I call that the candidate for D. So FD1 union FD2 is basically now the candidate for D. And then now this is the candidate. We now do a second pass of the database D and count those candidates and filter out any those that are not frequent. So in essence, we have done two scans. The first scan of the whole database, we brought it into memory, found all frequent patterns in each partition. Then we took the union of all frequent item sets that are found in all partitions. We called that the candidate for the entire database, and then did another scan, and we then found out the set of frequent patterns in the whole database. So now the question is, why is this required? So let's look at that. So generally when we say frequent, we mean that it supports the minimum support criterion. So when I use the database D1, D1 is of course smaller. So let me say D is equal to N is equal to 1, and similarly D2 is equal to N2. Okay? So of course N1 is going to be less than N, is a partition, right? So if I use a minimum support of 0.2, minimum support, not the count, 0.2, okay? So the absolute count that I will be looking for in my D1 would be 0.2 into N1 to make it frequent in N1, in D1. But in the entire database, we will need how many? 0.2 into N to make it frequent. So 0.2 into N1 would make it frequent in D1. Similarly, 0.2 into D2 would make it frequent in D2. And similarly, 0.2 into D3 would make it frequent in D3 and so on. But to make it frequent in D, it has to be 0.2 into N. So let's just take a hypothetical example. And of course, I'm talking about two only, D1, D2. So let's say D1 में हमने देखा कि AB frequent है, ठीक है? So which means that it occurs, and let me take some numbers also. So let's say these are 50 and 50, okay? And again, taking example, min support count, let's say 3, okay? So AB is frequent in D1, it means that it occurs more than 3 times. So let's say it occurs exactly 3 times. And it is not frequent in D2, okay? So let's say it occurs only 1 time in D2. So total times, so let me write this. So AB is equal, wait a second. Let me write D1. इसमें AB occurs 3 times, ठीक है? And D2, AB occurs only 1 time. It is not frequent in D2, it is frequent in D1. ठीक है? So total count कितना हुआ? Just 4. But to make sure that it's frequent in the whole database, which is of 100 example, it must be at least 6, because 3 divided by 50 is the percentage that we wanted. So for 100, it would be 6. So 6 to ye ho nahi raha, right? But it is frequent in D1. So that's why we took the union and do a counting again. So the other scenario would be, let's say if we have BC, इसमें भी 3 है, D1 में भी 3 है, or let's say BC, D2 में भी 3 है, दोनों में frequent. If it is frequent in both, then it's for sure going to be frequent in D. But if it is frequent in just one, then it may be possible that it's not frequent in the whole database. So that's why we do that candidate stuff and do a second scan of the database. So is this point clear?
Yes.
So the minimum support is actually 0.06. Okay? So 0.06 into 100 would be 6, but 0.06 into 50 is 3. Okay, so that was the partitioned a priori approach. You can use this approach if your data set is large and you just want 2 scans. You can break it into smaller pieces such that each part fits into memory. So that would be 1 scan for all frequent item sets in each partition, then take a union, which would be candidate for the entire database, and do another scan to finalize. So this, of course, will give you exact results, same as the original a priori algorithm. There is no approximation, there is no other errors in it. So the other approach is sampling. Let's quickly discuss this. We are running out of time. So in the previous case, we did partitioning. So let's say we had original database was D. We take a sample of size, let's say N1, which is less than N. ठीक है? Let me just use इसको S कर देते हैं. ठीक है? N is the full database size. So if you now find all frequent item sets in S, sorry, वो size लिखा है ना? एक second. S of size ठीक है, अब I think that would be clearer. So the sample is called S. Its size is bar of S. ठीक है? So Fs is the set of all frequent item sets in S. So how would this relate to F and D? Can we now have like strict boundaries, or you can say bounds, as they say in theoretical computer science? Because S is a sample, and sample generally would be simple random sampling with replacement, which means that the sample is at least somewhat representative of the original transactional database. And of course, we are sampling whole transactions, not individual items. Transaction sample कर रहे हैं हम. ठीक है? So if you find frequent item sets in S, how do they relate to the frequent item sets in the original database? Actually, there is no you can say strict relationship, because it is purely probabilistic. You might be able to find you can say most item sets, but not all. And of course, it will depend, of course, on the distribution as well. And generally, distribution is not known a priori, or it cannot easily be found as well. But this is a good way to get a good idea of the item sets in a database. So if you wanted to get a quick idea of the strong or the frequent item sets and the strong rules, you can take a sample of some reasonable size that you can process quickly and find all frequent item sets on it. Of course, this would not be exactly the whole item sets on the full database, but they will give you a good approximation. So this, as I said, is approximate, not exact, as opposed to the previous approach. ठीक है? So this was another way, another technique that you can use. And then finally, let's do one more, and then we'll stop for today, which is known by the name of dynamic item counting or item set counting. But of course, all of these are separate papers that were published earlier in 2000 or late 1990s. So, but these ideas are usually implemented in many implementations that are available today. So this idea is essentially this. So let's say you're talking about a specific transaction TK. So if a transaction TK transaction is a transaction in a database. So let's say, let me take an example. Let's say A, B, D, E, F. This is a transaction. So if a transaction does not contain a frequent, let's say 3 item set. So let's say मेरे पास एक frequent 3 item set है. Let me say D, C, D, E. So CDFS. So CDE is not present in this transaction. And we know that this transaction is frequent. So any superset of this item set would also be not present in this transaction, right? So ये present नहीं है तो कोई भी superset होगा, let's say any superset, like for example C, D, E, F would also not be present in this transaction. So what is done in this approach is, if we have found that a particular transaction, a particular item set is not present in a particular transaction, we basically label that transaction as, so we do not scan that transaction for counting next time because it will never contain any supersets of that item set. Okay, so do you get this point? So when we scan a database, we scan each transaction one by one. And from each transaction, we try to generate its subsets to check whether a particular item set exists in it. But if we have found at a previous level, let's say in this case, the level was A, B, D, I don't know, what did I write, the A, B, B, D, E, and F. So if BD3, level 3 is not present in this, then in future level, I should not count or use, look at this transaction again. Okay? So in other words, we are keeping track of transactions that contain frequent item sets. If at any point during our database scan, we found that a transaction do not contain any frequent item set, we just tick mark it or take its bit as 1, saying that it's no longer needed. We will not count it, we will not look at it. So kind of extensive scanning of transactions is reduced in this way, especially at higher levels. So of course you would have to do some bookkeeping. So you'll have to check transactions that do not contain the current set of frequent item sets, or even the current frequent item set, single frequent item set, or even the whole set of frequent items. So एक आपको बुक कीपिंग करनी पड़ेगी, और उस बुक कीपिंग का फायदा ये होगा जब आपको पता चलेगा एक transaction did not contain a particular frequent item set, you would not scan that transaction again. You will not load that transaction again and extract its subsets. Okay. So I think I would probably stop here. So any questions? Any questions? So no questions? Surely, I think we are out of time and there are only a few participants left. So let's end the session.